Yeah, so I would like to take this opportunity to explain a different mechanism to get emergent geometry from matrices, which is different from what we heard in the first talk of this workshop. So the first half of this workshop, which was mainly about holography and very sophisticated methods to obtain holographic geometric things from these matrix models. So this is going to be very different conceptually. So please try not to understand these things in terms of holography. Just try to understand it in terms of much more elementary field theoretic point of view, and there's much more local physics. And it's basically the mechanism of spontaneous symmetry breaking in gauge theories. That's what it really boils down to. Pages here. Okay. So so the starting point for me will be the IKKT model, which we have all heard about now. And so basically, I just would like to ask the question, is it possible to get anywhere near realistic or near, sort of realistic 3+1 dimensional physics from that model? And okay, to make the approach a little bit more well-defined, I would like to impose one further conditions. I would only like to consider scenarios where there are only finitely many degrees of freedom per unit volume. I mean, that's kind of, because otherwise things get out of hand, and probably most people would agree with this anyway. So I will only consider configurations with finitely many degrees of freedom per unit volume. Now that's already quite a strong restriction in a sense, because it tells me that we should not use the matrix model compactifications that people have considered in string theory. So for example, this Kohn-Douglas-Schwarz compactification of target space using non-commutative Tor and so on and so forth, all of these introduce infinitely many degrees of freedom per volume. And that sort of completely changes the field, and then the model is no longer non-perturbatively well-defined, and it becomes more like a field theory and so on. So that I don't want to touch. Okay, now if we don't want to do that, it means, okay, so we cannot compactify target space, and that already means that we cannot use holography, because holography will inevitably lead to a 9+1 dimensional gravity if you don't compactify the target space. And of course, this is very interesting, and we heard lots of interesting things about it, but it's just not the 3+1 dimensional physics. So what else can we do? And there is, in fact, another way to get 3+1 dimensions without compactifying the target space in the matrix model sense. And that's what I would like to explain. So, and this is kind of, it's just a different regime and a different, it's a different regime of this kind of model. Namely, I will consider only the weakly coupled gauge theory which arises on non-trivial vacua of the model. So the point is, I need some kind of non-trivial vacua, like in the Higgs effect in field theory. You just pick some vacuum with an interesting structure and then look at the gauge theory of fluctuations around that vacuum, and I will only discuss weakly coupled physics because that's the only thing I can reasonably do. So that's the regime to consider, and this is very different, of course, from the regime where holography works. Okay, so that's sort of to make the connection with string theory. Yeah. Yeah. Why do you? Well, if you look at all the proposals for compactifications of target spaces in the matrix model, they involve tori, and when you introduce tori, those are infinitely many degrees of freedom, because even the non-commutative tori, they have infinitely many degrees of freedom. Just look at them. And it's quite clear that's the only way to do it. You really cannot avoid that. Yeah, so I claim that all these things in string theory literature is always, you have infinitely many degrees of freedom. You can do it, of course, but it's a different ballgame. Yeah. 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 Okay. Basically, it just means that I should be able to talk about the finite dimensional matrix model. That's what I mean. So this will probably mean that the geometry will always be compact, and large n to infinity limit will always be understood in the sense of infrared regime, so making the volume large. So you don't, in other words, I should be able to describe, let's say the ingredients of this room with finitely many degrees of freedom. It's a very simple requirement. Yeah, exactly. Yeah. So I don't want to leave the regime of finite dimensional matrix models. orthogonal limits, but not, you know, these compactifications are really different framework. Okay, now, and so the first reaction might be, well, if you have a three-dimensional brane embedded in target space, somehow there is going to be, things will escape into the bulk, there will be 9+1-dimensional gravitons and so on, and so maybe this doesn't make sense. But actually it does make sense, and it does make sense precisely in the weakly coupled regime. And I claim that in this weakly coupled regime, really, there are no degrees of freedom which radiate off the brane. And it's very obvious if you look at it from the point of view of non-commutative field theory. So it's really a consistent way of looking at these things. Now, if you look at the non-perturbative regime, then yes, then you would have things escaping into the target space, and in principle it does happen, but it does not happen at low energies. That's the claim. Therefore, it's a consistent way of getting 3+1-dimensional physics from the IKKT matrix model without doing target space compactification in the usual sense. So that's sort of the first qualitative remark here. Now, having said that, it is of course true that quantum effects do induce something like type 2b supergravity in the bulk. And this is a holographic mechanism, and it is of course there. But this is really just a holographic dual, and it's not the physics, this is not what happens at the low energy physics. It's just a different way, or it's just a geometric way of describing some aspects of the effective action. And it means, from the point of view of the gauge theory of the brane, it just means that there will be short range effects which drop off like r to the -8 on the brane. But this means it's a kind of a, you know, this is really a short range correction. So the effect of the 9+1-dimensional supergravity will be some short range contribution to the low energy effective action, which is probably not visible. At least that's the hypothesis that I'm using. So this is just to make clear the relation with string theory picture. Okay, so now having said that, let's become a little bit more specific. So I would like to explain a mechanism which leads to 3+1-dimensional gravity on such a brane. But actually I have to step back a little bit, and it turns out it works only if you consider branes which have a product structure. So this would be a space-time brane, and there has to be some compact space which is embedded along the transversal direction, but it's really a compact space, and the whole thing is embedded in flat target space in some sense. So it's the uncompactified model, and I have to consider branes with a product structure like that. And moreover, this compact space, it has to be a fuzzy space, which means it should include only finitely many degrees of freedom. So something like a fuzzy sphere. So then that's in line with the requirement I gave you before. And that is actually, essentially turns out to get an induced Einstein-Hilbert action in the low energy effective action on space-time. So that will be the main message I will explain. Now, everything will work, everything I will compute will be ultraviolet finite. So there will be no ultraviolet divergences, at least at the one loop level, but probably even at higher loops. And again, so there is no compactification of target space in the string theoretic sense. So there is no landscape problem which pops up here. Okay. Yeah. Yeah, exactly, on the brane. Yeah. Okay, so yeah, and so what are these branes mathematically? So the structure is, you should think of these branes as quantized non-commutative spaces. So in other words, they're branes with a B field, and they're kind of quantized branes. So again, this is something which is familiar from string theory, and that's kind of, it's a natural, again, it's a natural framework in this context, because then you have the usual Bohr-Sommerfeld relation that the dimension of the Hilbert space, so the size of the matrices, is proportional to the symplectic volume of the brane, and that's exactly what I mentioned in the beginning. That's the basic assumption, that you have something like that. And also this class of backgrounds is closed under deformation. That's very important. So if you take some symplectic space and if you deform it in some small way, it's still a symplectic space. That's very important, and that's a standard property of symplectic spaces, and it means it's a reasonable class of backgrounds to consider. And well, again, I said there will be, well, there is no ultraviolet divergence, and related to that, there is no ultraviolet infrared pathology, which you have in generic models. And so that means in the IKKT model, because of maximal supersymmetry, this is actually, you get the reasonable low energy physics. So I'll come back to that. So this is sort of roughly the picture. And okay, let's be a bit more specific. So the model we have just discussed, I don't have to explain it anymore. So So there is, of course, the usual gauge invariance of matrix models, and this will give rise to all the gauge symmetries on the effective gauge theory on the brane. And we will just consider a non-trivial background of this model. So some kind of a given background matrices, and then study the small fluctuations around this background, just like you do in field theory. So this is a very, very natural procedure. And of course, I have to choose this background. In principle, you would like that the effective action of the matrix model at the non-derivative level chooses something like that for you. So that's kind of what we heard in the morning. But at the present stage, we are not there yet. So at the moment, I just have to pick some branes which I think are interesting and see if it is consistent, if they're stable, unstable, and things like that. No, I will give you an example where the time dimension is not compact. It could also be compact. There is also examples like that, yeah. Closed time-like curves can, in principle, you can write down something like that. Yeah. Okay. Now, if I look at this model and at the physics of fluctuations around such a background, now at the classical level, well, the brane will, of course, fluctuate. So it's some sort of a theory of gravity, but it's not general relativity. So I would like to call this pre-gravity. It's interesting, but it's not general relativity. And the point is that, well, of course, you have to quantize the theory. And once you do quantize it, and, well, you can only do it, well, I can only do it at one loop, sort of. And then you indeed see that in the one loop effective action, there is an Einstein-Hilbert term coming up, and we'll compute that. That's exactly what Schmidt was mentioning. So that's the main result. And in fact, this is the only model where this works, because the point is that there will be no divergences. So in some sense, the Newton constant will be finite. If you would do this exercise in any other model, it would be a complete disaster because of ultraviolet infrared mixing. So all of this only works in the maximally supersymmetric model. That's very important. Okay, so this is the background, and I will add the most general fluctuations.
Total tilde plus 1.
Yes, yes. Exactly. You mean that you get the incident? Yeah. Well, it requires, it doesn't depend on the details of the brane, but it requires this product structure. So you need a space-time brane with 3+1 dimensions and some compact space in the transverse direction. That's all. Yeah. So the specific structure of the space-time brane is not really essential. And also the specific structure of the compact space is not important. No, it wouldn't work, because then if you work at one loop level, then you have ultraviolet infrared mixing, and what it really means is that the effective low energy action is completely non-local, because then you have sort of long string modes which run in the loops and they dominate the loop at the effective action, and that means that the low energy action is completely non-local. It just is not acceptable. So, I mean, of course, in the three-dimensional models, well, 2 dimensions is kind of harmless. That would still work probably, yes, but even adding a mass term is not allowed. Even a mass term would create very serious problems. Or at least it has to be parametrically small. And the BMN, of course, would work because it's maximally supersymmetric. But that's amazing. So if there is a pure matrix model version of BMN, that would work. Yeah, then that's very interesting. Yeah, then it would work, yes. In fact, I would like that's an interesting thing to consider. Okay, so the outline, let's see how much time I have. So first I want to explain briefly the geometric interpretation of such a background, and we'll see structures like a frame and a metric and torsion in a certain sense coming up. And then I will discuss how to compute the one loop effective action, at least roughly. And I will probably not have time to discuss an explicit example of a quantum spacetime with very nice properties, which is sort of has lots of covariance. I will only mention it briefly, but in fact, this is not really essential for the mechanism. Now, for literature, I mean, some sort of, as a starting point for this geometric structure, maybe this is a little short review. The one loop computation is here, but lots of details will be in the book, which should come up very soon. Now, so let's discuss the geometry of such a background. So here's the bosonic part of the model. And well, first of all, why is it reasonable to consider symplectic spaces? The point is that, at least in the Euclidean case, the action is the square of commutators. So the low energy contribution to the action are probably matrix configurations where the commutator is small in some sense. And now it's sort of a reasonable thing that if the commutator is sufficiently mild, then it's probably a good idea to replace commutators by Poisson brackets like you do in quantum mechanics. I mean, one can discuss how general this is and so on. I don't really want to spend time on it. So let me just focus on backgrounds which allow a reasonable interpretation as, as quantized symplectic spaces, which means the algebra of functions on a symplectic space then corresponds to the space of operators like in quantum mechanics. The commutators, at least the commutators of nice operators, should correspond to Poisson brackets and so on and so forth. So let me just restrict myself to that regime before trying to justify it. Now, if we assume that we have a background which assumes that, then it's easy to understand the meaning of a matrix itself. Because then each of these matrices, well, it's an operator, therefore it's a function, corresponds to a function on a brane. Now you have 9 plus 1 of these matrices, so that and this of course just describes the embedding of this symplectic space into target space. So that's kind of the obvious geometric interpretation of such a background with reasonably nice behavior. And again, if you deform that, it will just deform the brane, and it will not do anything dramatic. Okay, so again, so this is the usual correspondence which you know from quantum mechanics. I just mentioned it. The trace corresponds to the symplectic volume. By the way, you have to be careful, and it's very important that this relation, strictly speaking, can only work at low energy. So this is only in the infrared regime. There's always, so what one really has to do, you need to consider configurations which have a sufficiently large infrared regime where this correspondence really makes sense as an approximate isometry. It will never work for the full algebras. So because this contains string modes and this does not. So one has to be careful. But again, yeah. Yeah, it's the non-commutative structure. So it's the commutator of matrices. This is the Poisson bracket, and that's the dimension for quantity. That's like h bar in quantum mechanics. That's the scale. Exactly. Exactly. So a given background will define your scale. The model itself does not define your scale. Yeah. Only on a background. The model itself has no scale. That's important. But the background sets your scale. Yeah. That would, yeah, in the example of the fuzzy sphere, exactly, it would be one of these large spin representations. And if you take the matrices to be angular momentum generators, yeah, yes, then this gives you a fuzzy sphere embedded in target space. That's an example, yes. It works more generally. Okay, so this is the setup. Now, okay, very quickly, how do you get geometry for this? Now, how do you measure geometry? I mean, geometry is really tells you how things propagate. So you put the fluctuation on a brane, some excitation, and you see how it propagates. So the propagator encodes the metric, which means you have to look at the kinetic term. This is the kinetic term for basically all the fluctuations you have in a matrix model, if you think about it. And well, how to understand it is very simple. This is a commutator. So you replace a commutator with Poisson bracket. I write phi as a function of x. So phi is phi of x. Then this commutator can be written in terms of this Poisson bracket. And then this takes the role of an effective frame. So you can write this in a semi-classic limit in that form. So these are first order differential operators. And two e's contracted with eta, that's of course then the metric. So it's very easy to see. You can write in a semi-classic limit the kinetic term generically in the standard form with an effective metric. The effective metric is given in terms of the frame. And the frame is really the symplectic vector field generated by the matrices. So that's really the main thing. Frame is the symplectic vector field generated by the matrices. That, in fact, that's already a bit funny because it means that there is not going to be manifest local Lorentz invariance because it's an easy thing. Any frame of this sort will always be divergence free in this sense. By the way, there is also a dilaton which you can identify. Did I write it down? Yes, so the dilaton has to do with the symplectic density and so on and so forth. So anyway, so these frames are kind of gauge fixed in the usual sense, which is an indication that there are more degrees of freedom than in GR. But it's perfectly consistent. And it doesn't mean that Lorentz invariance is really broken, it's just kind of gauge fixed. Okay, so this is the effective metric. It governs all the fluctuations, therefore it's sort of a gravitational thing, but you should understand the dynamics of this geometry. Also, by the way, this is also the metric which couples the coupling fermions on the background are essentially governed by the same metric. This will be discussed briefly in a later talk today. Okay, so now one would like to understand the dynamics of the geometry. So the equations of motion of the matrix model are very strange, and so they look strange. And to translate them into conventional language is not easy. And it turns out the most useful, well, I think the best way to do it is to consider not the Levi-Civita connection, but the Weizenberg connection, which is associated to the frame. Because the background defines a frame, and for each frame you can define a unique Weizenberg connection just by declaring this frame to be parallel. It can always be done. That's a connection which is metric compatible, and it's flat, but it has torsion. So it's just a different way of doing geometry. You get used to it. And the reason why this is a good concept is because of the following identity. You can show using the Jacobi identity that the torsion of this connection can be written in terms of Poisson brackets like that. So this is the commutator of the matrices. So the torsion is a very natural object in this context. That's an important identity. And it encodes, in some sense, the field strength of this non-commutative gauge theory, and here it has a geometric meaning. So we will use this identity at some point later. So just maybe notice this briefly. Now, okay, now given this connection, you can write, these are the equations of motion of the model if you put the mass term just for fun. And it turns out you can now write it in a geometric way like this. So this is now a tensorial equation, and this is the Weizenberg connection. So that's a nice equation. By the way, it turns out to be equivalent to or formally, it looks the same as an equation discussed by another Kawai Kimura, but the setting was completely different. But yeah, nevertheless, so this kind of equation pops up naturally, it seems. And now once you have this, it's still strange because the Weizenberg connection, but now you can translate it in terms of the Levi-Civita connection, then it looks like that, and it involves the totally antisymmetric part of the torsion. And anyway, so you can find some nice equations for that. And then you can also try to solve them. If we found some solutions. But whatever it is, it's not GR, of course. But to try to make the connection to GR, first of all, there is a nice identity. So this is really an identity. You can write an Einstein-Hilbert action in terms of distortion, always like that. This is basically well known from the context of daily parallel gravity. There is some extra terms. This has to do with the totally antisymmetric part of the torsion. Now, and another thing you can do is you can compute the on-shell rigid tensor just using the classical matrix model. And well, it's not zero, but it turns out to be this quadratic expression in terms of the torsion. And that's interesting for the following reason, because it tells you that if you start with a flat background and if you do linearized metric perturbations, then the linearized metric perturbations are actually Ricci flat. That's a funny thing, but at the nonlinear level, they are no longer Ricci flat. So that shows you it's certainly not GR. So, sorry, what is the solutions? I mean, this is an identity. Yeah, exactly. There are more degrees of freedom. The degrees of freedom are different from GR. I come into that. There are more degrees of, well, it depends on the background. Yeah, that's a non-trivial point. Absolutely. Yes. I will I'll briefly discuss it perhaps. Okay, now let me make one more comment. Let me compare. So the original matrix model action, you can write it like this. Remember, theta is just the Poisson bracket of background. So this is how the original matrix model action looks like. Now, the identity which I just shown you for the Einstein-Hilbert action was in terms of the torsion, and the torsion, this is a quadratic contraction of the torsion, and the torsion is a derivative of this theta thing. So that means the Einstein-Hilbert action has two derivatives more than the bare matrix model action. So that's a very strange and interesting thing, because usually in the conventional framework, there is no action that you can write on which has fewer derivatives than the Einstein-Hilbert action. Here you have. And that's the whole point, because it means that this action is much better behaved under quantization. And that will be the message. So we're quantizing this action, and that's something which makes sense. And the Einstein-Hilbert action will pop up in the quantum effective action. So you don't have to quantize it anymore. So that's basically maybe the main message here. And another thing is, of course, that in the infrared regime, you would expect that the bare matrix model dominates rather than the Einstein-Hilbert action. So you would expect that the cosmology will be governed by the bare action and not by the Einstein-Hilbert action. And this indeed seems to be the case. So there are very nice cosmological solutions of the matrix model, which are reasonable without having to do any fine-tuning. And I think this is an interesting thing. All right. Yes. Now, just how much time do I have? Not much, probably. 15? Okay, that's reasonable. Yes, so well, these kind of backgrounds, yeah, you can also find linear Schwarzschild solution, but okay. Let me discuss the one loop effective action. Yeah. Yes, they're bouncing cosmologies. Yes. At least I think that's the best interpretation. Yeah, we have. In fact, Emanuele will discuss one of them a little bit later. Yeah, I'm not sure how to pin it down, but the action. Well, in some sense, it's because I think it's because of supersymmetry. So we know that the action has a flat solution. So the flat T3 brane is an exact solution. It's even PPS. So that we know. And these are, well, they're different, but they're just mildly curved. And that already tells you that there is no cosmological constant, even at the quantum level. So this story is very different. And it's possible in this framework, you can have reasonable expanding cosmologies without such fine-tuning. And this is actually not so bad, by the way, at least as far as my naive picture understanding goes. Anyway, now I would briefly like to discuss how can you compute the one-loop effective action. Now, so in fact, it's not a surprise because this is a general story which goes back to Sakharov of induced gravity, which is the statement that if you quantize any theory on a background with curvature, you always expect the Einstein-Hilbert term to pop up in the effective action. But of course, usually you have to put the cutoff, because usually this is lambda squared, there's a cutoff. And that's the whole point. This is a variant of this mechanism where you don't have to put the cutoff. It's automatically, it's finite. So, and in fact, you can compute the Newton constant here. And it turns out that the Newton constant is essentially the Kaluza-Klein scale of these fuzzy extra dimensions. And that's also why you need them. Otherwise, this term just vanishes. So that's what happens at one loop. And technically, we'll discuss very briefly what you find is this thing. And then you can translate it into this form. And that's what really comes up from the computation. So let me very briefly just hint how to compute these things. It's of course an approximate computation, but I think it is reasonable. So what do you do? Well, in principle, of course, you should just compute the integral over matrices, as we have heard many times this morning. I will use the regularization of the Lorentzian model by adding infinitesimal Euclidean mass term. Then it's the integrals are well defined, and this is fine for one loop. So then we just use the usual one loop story, so just compute the Gaussian integral around one of these, or around some given background, and the background I will just denote with y, and the fluctuation is some sense a, and you just have to do the Gaussian integral over all the fluctuations. And this, of course, boils down to the usual, it's just a trace log formula. In this case, it's a bit complicated because there are bosonic, fermionic, and ghost contributions. And now the whole point is the following. Because the model is maximally supersymmetric, the first three terms here, if you expand this, they cancel identically. And this is totally crucial. And that's the only reason why you don't have ultraviolet divergences. So the leading term is, in some sense, is the n equal 4 term in this expansion, which is quite a mess. So this is a complicated thing, and that's what we have to compute. And you see, then this has 1 over box to the 4. That's the reason why it's finite in 4 dimensions. If you don't have these cancellations, all of this stuff gives you a terrible mess, which is not acceptable. Okay, so we should somehow find a way to compute this, and this is the hard part, of course. And there is a trick to do it, and the tool to do it is to use what I like to call string modes. So this is now we come to the stringy nature of matrix models. It turns out that, well, loop computations are typically dominated by, well, let's say high energy modes. Now, the high energy modes here are typically not functions, but they are sort of like strings, starting at one point and ending at another. And you can realize them in terms of coherent states on your background in this way. So let me assume that there is a nice set of coherent states on the background, which usually you can write down even explicitly. Now, using these string states, there is an exact formula for the trace, and that's what I will use. So the trace of our operators can be written in a geometric form like that. So that's the formula which I'll use. It's easy to prove. And then, yeah, and that allows you to give in fact, the point is this gives you the effective action in position space. So you don't even have to do Fourier transform, which you cannot do. So this is a tool which gives you an effective action in position space. It's very nice, actually. It's much nicer than what I've seen otherwise. And the reason why it works is the following. These string states, they sort of almost or approximately diagonalize the commutators. So if you compute commutator of a background with this thing, it essentially gives you the difference of the beginning and end point of these states. And also the box operator acting on this thing gives you essentially the distance between these states. So the sort of the energy is like the length square and so on and so forth. So this is all very reasonable. And that's in this way you can approximately evaluate these integrals. And yeah. By the way, let me make a remark about this story is closely related to ultraviolet infrared mixing in non-commutative field theory. You can use this same identity, which I've just shown you, to compute the non-planar contributions to the effective action in field theory, and you find immediately after one line this form. And that is, of course, you see, this is a non-local quadratic action with this kind of thing, and that's something which is completely unacceptable. And that's ultraviolet infrared mixing. It means you have it's not the local theory anymore, and these things will be cancelled due to symmetry. And then what's left over is a version of that where you have 1 over x minus y to the 8, and that's then acceptable. Okay, so you just apply this formula and somehow do a sort of a by hand. You just use these geometric approximations to these terms, and then you can do it, and you can write this trace log in the geometric form like that. It's still pretty complicated. There's a lot of terms, but you see this goes like 1 over x minus y to the 8th power, and that's of course what you expect from supergravity. Indeed, you can derive sort of the type 2b supergravity in this way. I mean, at least some basic elements of it. But we want to, okay, so how to get the Einstein-Hilbert action is still not obvious, so we have to massage this a little bit further, and we have to, well, what do we have to do? First of all, notice that these integrals are convergent. That's obvious. So they're kind of local. And now that means we can, but we want to get now sort of the fine details of the geometric dependence of these things. We have to compute that. So now I have to refine this basis of string modes in something in wave packets, and there is a nice way to do it as follows. Namely, you can consider, if you consider superpositions of these string states, which are smeared a little bit, but with the same distance, but you smear it and make a Gaussian envelope on the position, then these are modes which correspond to Gaussian wave packets. And there is a precise way to show that. So this is really a correct statement. And then you can use these as a overcomplete basis of function to compute the trace. It's exactly the same identity which I've shown you before, but it's more useful because now these are now low energy. You can make the wavelength sufficiently low such that they really become local eigenmodes of the box operator. So the box is then locally something like gamma mu nu, and also these commutators, you can now rewrite them in terms of Poisson brackets. So that's the technical step to evaluate these things approximately. In other words, you take the trace formula which I've shown you, you translate it in terms of this basis, and it becomes an integral over space-time and an integral over modes, and this is what you can now compute explicitly. And what you find is, yeah, so the first thing you find is, well, you don't get an Einstein-Hilbert action if you don't put this extra term, because you get the fourth derivative action because you had 4 Poisson brackets. Now the trick, as soon as you put a background which has some compact space in transversal direction, then there are some mixed terms here which are 2 derivatives on the space-time and 2 derivatives on this internal space. This arises because of this term here. So you see here, you have, these are sort of fourth order terms these are kind of, I've not written it very well, these are four brackets and they're four derivative terms. Now, if you have this background with the product structure, then you can evaluate, if you evaluate this is a double bracket, you can evaluate it using the trick I showed you before. Now, this is the torsion which I've shown you in the beginning. So what you get is a contraction of the torsion, and if you put everything together, crank a little bit, then the one-loop effective action contains this term. That's a contraction of the torsion, and some constants which are essentially determined by the Kaluza-Klein scale of this K with large numbers. And this you can then rewrite as Einstein-Hilbert action plus an extra term. This has to do with the antisymmetric component of the torsion. And that's of course a correction to Einstein-Hilbert. And it depends if this is an independent degree of freedom or not, depends on the type of background you have. It may be a new degree of freedom. It may be determined by the geometry. It depends on the class of backgrounds. Anyway, I think that's a fairly universal computation. You get this kind of thing. Okay, so this is the main result. Yeah. Okay, this thing? Yeah, okay. So these are approximate plane wave with wave number k. So you get these things, and then they have to integrate. Let me go back one step. You see here, the trace is an integral over x and also over k. So integrate over k, and then if you integrate k mu, you get g mu, basically, because that's a lot. If you evaluate it locally, you can really compute that. And to do these integrals, by the way, it's important to have the I epsilon regularization, which is the epsilon term which I showed you in the beginning. But then you can sort of, at least formally, you can carry out these computations and you find this thing. Now let me just very briefly, so this is the bottom line. The one-loop effective action in the infrared limit includes an Einstein-Hilbert action term plus some other terms. You can compute the effective action. It's set by the Kaluza-Klein scale of this extra dimensional thing with some, these are large numbers which depend on the structure of K. Okay. So that's the one thing. Now, the other thing is, of course, there are extra terms in the one-loop effective action. Of course, there is also vacuum energy, it's clear. In fact, it's large because supersymmetry is spontaneously broken. It's large but finite. But the structure of this, it's not a cosmological constant. That's the point. Because it doesn't come out as an integral over square root g, but it comes out as an integral over the symplectic volume form, which is rigid, and the diladon. So the diladon enters here, and also the scale of the Kaluza-Klein guys. So it is some large contribution which will determine the structure of the vacuum, but it's not a cosmological constant. So I don't completely understand it, obviously. But one thing you can actually do, and this is sort of this is really a result. If you collect these terms as a function of this is essentially the radius of this extra dimensional space, actually you have a non-trivial minimum. So there really is a stabilization of this extra compact space at one loop. So I think that's a correct statement that you find in the one loop. So that sort of means that assumption of having extra dimension is at least self-consistent at the one loop level. Okay, so that's basically, yeah, this is the result which I wanted to explain. You mean as a function of time? That's a good question. So if on the cosmological background, we are looking at this right now. No, it depends a bit on time. There is a time evolution of these things. At least, both the dilaton and all these things in principle will evolve with the cosmic expansion, and we are actually trying to work this out a little bit. It's complicated. It's complicated. To do this Euclidean way. Yeah, I guess you could do Euclidean, you have a bit the issue that you don't have the Majorana-Weil fermions, you don't make sense. So in principle, I guess in principle, somehow, if you handle some subtle things properly, you could. The structure should work, yeah. Okay, so that was mainly, well, maybe again, so one last remark, I said it before. So the total effective action is, of course, bare plus one loop. And the thing is that in the extreme infrared regime, so cosmological regime, you would actually expect this to dominate. So there should be some crossover behavior between some regime which is more like GR, or at least close to GR, which is on not too long scales, and then at the cosmic scale, I would expect that this will dominate. But I cannot give you any numbers or any you know, this is just structural observations for the time being. Okay, so this is the main result. Yeah, there's the story, of course. I did not tell you what is the structure of this space-time brane. Now, if you do this on a simple-minded, like a Weyl quantum plane, in principle the calculations work, but then there's a bit of an issue, or it's a big issue, because you have a B field which breaks Lorentz invariance, and that's at least uncomfortable. So, but you can avoid this. There's a class of somewhat more sophisticated branes which have an internal structure. So it's like a space-time plus an internal sphere, but it's not a trivial bundle, it's an equivariant bundle, which means the local Lorentz or the local rotations act on the fiber, and as a result of that, but there is no B field. So there is no rank 2 tensor which explicitly breaks Lorentz invariance on the brane. So there are explicit such background. They're very nice. In fact, it's quantized twistor space, and Tung will say something about that. And then, yeah, you don't have an explicit Lorentz breaking tensor, so it looks quite appealing. The price to pay for this is you get the higher spin theory, and Tung will maybe explain that, because the internal harmonics of that actually become higher spin modes. So you get some funny higher spin version of gravity, where all the standard modes are amended by a Dauer of higher spin modes, which would probably decouple at low energies, but all of this remains to be understood. And one final remark is that in this framework, you actually get the full volume-preserving diffeomorphism as part of the gauge symmetries. Because the symplectomorphism work on this 6-dimensional space, that's a symplectic space, and then the symplectomorphism on the whole space contain actually all volume-preserving diffeos on space-time, which is kind of nice. And you can also show that there are no ghosts here. But it's very nice, but very complicated. It needs much more work. I'd appreciate any help. Let me skip this thing. So this is just, there's a lot of group theory behind these backgrounds. So this is all very nice group theory, but I want to skip these technical details. It's just a story that you get a higher spin theory on these backgrounds. Yeah, so let me summarize. So I claim that gravity arises at the one loop level in the quantum effective action, fairly generically, as long as you have product structure of space-time with some compact brane in x2 dimensions. The cosmological constant problem is at least not the standard one. It manifests, so vacuum energy has a different physical meaning here than in GR, and that's a good thing. There should be some crossover regime between some regime where hopefully the Einstein-Hilbert term dominates and becomes hopefully close to realistic, and some other regime which may govern cosmology. And there is also a nice class of background where at least the rotation invariance is completely manifest. You really don't break, there is no tensor which breaks rotation invariance. Local Lorentz invariance is not manifest, and that in some sense needs to be verified if it isn't broken in some funny way, but I don't see any hints that it should be broken. So I think effectively it should be close to respecting the local Lorentz invariance. But you get the higher spin gauge theory here. And there's lots of degrees, so on this kind of background, you have lots of new degrees of freedom. There is an axion, there is a diladon, there is higher spin modes of all sorts, and so this is complicated. Anyway, the point is this is a bit like doing string theory without compactification of target space, and I claim that in this framework, so weak coupling around a brane, this actually makes sense as a 3+1-dimensional theory. So maybe let me stop here.